Traditional data lake analysis requires complex extract, transform, load steps just to read the data. DuckDB eliminates this latency by operating directly on the source files. We are installing DuckDB locally using Python's pip package manager, ensuring the version supports the necessary extensions for object storage access. The core requirement for querying remote data lakes is the HTTPFS extension, which enables secure communication with S3, Google Cloud Storage, or Azure Blob Storage. Execute install HTTPFS and then load HTTPFS immediately after installation. This setup allows DuckDB to treat remote Parquet files as local tables, minimizing data movement and maximizing query efficiency right from the start. This in-process analytical database architecture fundamentally changes how ad hoc analysis is performed against massive datasets. Accessing S3 requires configuring credentials within the DuckDB session environment. Use set S3 region to specify the bucket location, for example, US-East-1. Authentication relies on either environment variables or explicit configuration using set S3 access key ID and set S3 secret access key. For production environments, always prioritize identity and access management roles or temporary security credentials over hard-coding static keys directly into configuration files. Once configured, verify connectivity by listing a known bucket path using the built-in glob function, such as select asterisk from glob/s3/mylake-bucket/data/**. This confirms the security handshake is successful before attempting complex analytical queries against the data lake files. The primary function for data lake interaction is read Parquet. This function automatically infers the schema from the Parquet metadata header, eliminating the need for manual schema definition. To query a partition dataset, use wildcards in the path argument, such as s3/mylake/events/year-2023/**.parquet. DuckDB intelligently scans only the necessary metadata blocks across the specified partitions. Crucially, always include a limit clause during initial exploration, such as select asterisk from read Parquet path limit 10. This prevents accidental full table scans on massive datasets, preserving both time and cloud storage costs while validating the data structure and accessibility.
Performance optimization hinges entirely on predicate pushdown. When a where clause is applied, DuckDB pushes the filter condition down to the Parquet reader before data is transferred. This means only the required row groups and columns are loaded into memory, drastically reducing input-output operations and network latency. For example, a query filtering by a timestamp column, where event time greater than 2024-0101 will only read the relevant data blocks containing those dates. Ensure your Parquet files are written with appropriate statistics and sorted columns, especially on frequently filtered fields, to maximize the effectiveness of this optimization technique and achieve near-instantaneous filtering. Data lakes frequently contain complex nested structures, often originating from semi-structured logs or JSON payloads stored within Parquet. DuckDB handles these using its struct and list types. To access nested fields, use the dot notation, similar to accessing object properties in programming languages. For instance, to extract a field named userID from a nested column metadata, the syntax is metadata.userID. If the nested data is an array or list, use the unnest function to flatten the structure into separate rows. This transformation is essential for enabling standard relational joins and aggregations against elements within the complex types. While direct querying is fast, creating temporary views simplifies complex analytical workflows and improve readability. Use create or replace view to define a persistent logical layer over the external Parquet files. This view definition stores the read Parquet statement and path configuration, allowing subsequent queries to reference the data using standard table names. For frequently accessed aggregated subsets, use create table as select, or CTAS, to materialize the data locally within DuckDB's in-memory storage. Materialization achieves sub-second query times for repeated analysis, trading storage space for significant performance gains on repetitive tasks.
Data lakes often contain legacy CSV files alongside optimized Parquet formats. DuckDB supports direct querying of CSV using the read CSV auto function. This function automatically detects delimiters, headers, and column types based on sampling the file content. However, CSV lacks the inherent metadata and statistics of Parquet, making predicate pushdown less effective and requiring more data transfer. Always specify the expected column types explicitly when performance is critical, using the columns parameter within read CSV auto to override potentially incorrect type inference and ensure data integrity during the read operation. This minimizes the risk of type mismatches during subsequent joins. DuckDB excels as an in-process transformation engine, allowing analysts to perform lightweight extract, load, transform operations without relying on external Spark or distributed clusters. Use it to calculate daily aggregates and write the results back to a new Parquet file in the data lake using the copy statement. For example, copy select date trunk day event time count star from events group by 1 to s3/mylake/dailysummary.parquet format Parquet compression ZST. This pattern enables rapid data refinement directly at the analyst's workstation, creating derived datasets that are immediately available for downstream consumption by other tools or systems. For production deployment, embed DuckDB within a Python or R application using its respective application programming interface. This allows system analysts to integrate data lake queries into scheduled workflows or microservices that require fast, localized analytical capability. Remember that DuckDB is an in-process database. Its performance scales directly with the resources of the host machine. For large-scale shared access, consider integrating DuckDB into a serverless function environment like AWS Lambda or Azure Functions for cost-effective burstable query execution against the data lake, ensuring the database instance is initialized and closed correctly within the function lifecycle.